In our previous video, we defined the operations of addition and multiplication of complex numbers, and we saw how the system forms a field. Now, using these field properties or field axioms, one can prove further algebraic properties, which is what the third section is about. We have seen two sections already, so I am leaving the third section to you. Instead, let's see this fourth section where we are going to see the modulus or absolute value of a complex number. Moduli is the plural of modulus, just like radii is the plural of radius. The authors start like this: it is natural to associate any non-zero complex number z whose real part is say x and imaginary part y with a directed line segment or vector, this vector, from the origin to the point x comma y, which represents z in the complex plane. That means this point is representing the complex number z in the plane. We call the ordinary two-dimensional plane the complex plane once you have identified a complex number z with this point, where the x coordinate of the point is the real part and the y coordinate is the imaginary part. And with this complex number, you not only associate this point, but along with it a vector also comes, which you can also think of as the position vector of this point with respect to the origin. This is exactly like how we associate real numbers with points on the real line. In this case, we don't have just a line, but we have all the points lying in two-dimensional plane. All of them we need for associating with the complex numbers, so that the complex numbers get a geometric representation. And with this association, we sometimes also call the complex number z the point z or the vector z. And this association is not just merely a superficial association, it brings out this fact also. It turns out that complex addition of two complex numbers, corresponds to vector addition, and complex subtraction corresponds to vector subtraction. And what this means is this: say you have two complex numbers z1 and z2. z1 is x1 plus iy1 and z2 is x2 plus iy2. Then you know how the addition works. z1 plus z2 will be x1 plus x2 plus I times y1 plus y2. So that means this is the real part and this is the imaginary part of the sum. So corresponding to this sum, there will be a point in the plane, and that point is this point, whose x coordinate is x1 plus x2 and y coordinate is y1 plus y2. And say the other corresponding points corresponding to z1 and z2 be this and this in the plane somewhere. It turns out that the vector that you get joining O and this point is actually the sum of these two vectors, which represent respectively z1 and z2. So in one hand you are adding the complex numbers using the algebraic definition, which is the definition of addition, and then you associate that sum with the point, and also then you are getting a vector. In the other hand, say you only consider the vectors and consider their sum using parallelogram law or triangle law, whichever, ultimately they give the same vector, which is this diagonal of this parallelogram. That is vector addition. And these two things match exactly. It's a fact, okay? We are not going to go into the proof of this, but it's a fact. So in that sense, complex addition corresponds exactly to vector addition. Now instead of addition, if you consider subtraction, say you consider z1 minus z2, then by the definitions we have already come across, that equals this: x1 minus x2 plus I times y1 minus y2. Now correspondingly, you will get a point, this time also in the complex plane, whose x coordinate will be x1 minus x2 and y coordinate will be y1 minus y2. That turns out to be this point. How do you get this point in the plane? Well, you can follow the vector addition, the vector definition of subtraction. So what you first do, you see the point corresponding to the complex number minus z2, because by definition this difference is the sum of z1 and minus z2. The point corresponding to minus z2 has these coordinates minus x2 comma minus y2. So you look at that point which will be opposite to this one. Opposite to this one means with respect to the origin and along this line at the same distance from the origin that this one is. Okay. So that means this vector is representing your complex number minus z2, and then you add this vector and this vector using your parallelogram law of vector addition. You get this vector, and that point, that tip of the vector, the terminal point of that vector is exactly the point whose x coordinate is this and y coordinate is this. So that's how complex subtraction also corresponds to vector subtraction. And you may notice one more thing from this diagram, and that thing is this. What you do, you join the points whose coordinates are x1 comma y1 and x2 comma y2. That means in the complex plane you are joining the points z1 and z2. This is the point z1 and this is the point z2 using a straight line segment. The thing you notice is that this vector which represents z1 minus z2 is parallel to that, and not just that, it has the same length. This is also a parallelogram. So that means if you translate this vector or slide this vector parallel to itself in such a way that one end coincides with this point, then the other end will coincide with the point z1. So we are going to remember this, because using this fact we are going to define distance between two complex numbers. And then finally we come to the definition of modulus. The modulus or absolute value of a complex number z, which is equal to x plus iy, is defined by this equation. This is the notation for the modulus of z, which is identical to how we write the modulus or absolute value of a real number. We just enclose it within two vertical bars, and the definition is this. By definition, this equals the square root, non-negative square root of x squared plus y squared, real part squared plus imaginary part squared. Note that this is always a non-negative real number. Non-negative I say because it can be 0 or it can be positive, but it will never be negative, and that too it will be 0 only when both x and y are 0. And that case corresponds to the complex number 0, which means that for the complex number 0, the absolute value is 0. But if the complex number is non-zero, then the absolute value is a positive real number. Now, what does this quantity correspond to geometrically? Because we have identified complex numbers with points in the plane, so this should have some geometric meaning. The geometric meaning is this. Say you consider the complex number z2. I am not considering z1 because this part is a little messy. So this point is the one that corresponds to z2. So corresponding to z2, what will be this quantity? That means what is the modulus of z2? Square root of x2 square plus y2 square, which you know from your analytic geometry is the distance of the point from the origin. So that's the geometric significance of the modulus of a complex number, that it calculates the distance of the point which corresponds to the complex number from the origin. And if you see it in terms of vectors, the complex number also is corresponding to this vector, then this is the magnitude of that vector. Note that if the imaginary part is 0, then our complex number is just the real number x. So here these bars indicate complex modulus. So we apply that definition, but then that gives us this in this special case, which we already know from calculus equals the absolute value or modulus of the real number x. So that means this definition of modulus of complex numbers is a generalization of our familiar definition of modulus of real numbers. Now with the geometric meaning of modulus available to us, we can make sense of this inequality, this type of inequalities geometrically. When you think of Z1 and Z2 as points in the complex plane, this inequality means that Z1 is closer to the origin than Z2, because this is the distance of Z1 from the origin and this is the distance of Z2 from the origin. For example, the absolute value of minus 3 plus 2y is square root of 13, which you can calculate yourself. It's a simple thing. And the absolute value of 1 plus 4i is larger, square root of 17. So this complex number is closer to the origin than this second one. Now next, in terms of modulus or absolute value, we define the distance between the two complex numbers Z1 and Z2 to be the absolute value of the difference Z1 minus Z2. Algebraically, suddenly this may not make sense, but when you look at the geometry, you understand why. What did we see just now? The geometric significance of absolute value, that whatever complex number you are having, whose absolute value you are taking, that complex number corresponds to a point in the complex plane. The absolute value is the distance of that point from the origin. Now in this figure, what is the point Z1 minus Z2? This one. So its distance from the origin should be this length. And what did I say just now? That this length is the same as this length, which turns out to actually be the distance between the 2 points, one representing Z1 and the other one representing Z2. So now it makes sense why we are defining the distance between Z1 and Z2 like this. And if you still have some little doubt about this definition, you calculate this, you know the real part and imaginary part of this difference, so the absolute value is this. Now you know this formula from analytic geometry or coordinate geometry as the formula which calculates the distance between these 2 points. So do you see how nicely everything has fallen in place in a perfect harmony? Everything. The geometric representation of a complex number, its vector representation, addition of complex numbers match with addition of vectors perfectly. Distance as defined like this matches with distance between the corresponding points in the plane representing those complex numbers perfectly, everything. So with this idea of distance, we can now do this type of things. We can consider a circle in the complex plane whose center is, say, at the complex number Z0, or more accurately at the point which corresponds to the complex number Z0, and say whose radius is r, which of course is a positive real number. Then that circle will have this complex equation. What is this equation telling you? It's telling you that Z is some complex number whose distance from Z0 is equal to r. The circle is the set of all points in the complex plane whose distances from Z0 is equal to r. Here Z is a variable complex number, a complex variable. Just like we have real variables, this is a complex variable which changes and takes on different complex number values. For example, you consider this equation. The modulus of Z minus 1 plus 3i is equal to 2. If you express this in this form, then it will be the modulus of Z minus of 1 minus 3i, that is equal to 2. So this is the complex equation of the circle whose center is at this complex number 1 minus 3i and whose radius is the positive real number 2. And finally, we are going to see some inequalities involving complex numbers and absolute value. We consider this identity. If you take the square of the absolute value of Z, then that becomes x squared plus y squared, or square of real part plus square of imaginary part. Note that although you have a complex number here, but the quantities on both sides of this equation are real numbers. In particular, this is also a real number. It's the square of the real number which is imaginary part of Z. And as such, this is greater than or equal to 0. So that means if you do not write this and simply write real part of z square, then possibly you are writing less. Possibly I say because this may be 0, in that case you are not writing less, so there is a possibility for equality. Otherwise you are really writing less. In that case this will be less than the left hand side. So that's how you get this inequality, which will give you something else also, which is this. If you lift the squares from both sides of this inequality, you get this inequality. The absolute value of real part of z is less than or equal to the absolute value of z. But we already know that for a real number, the absolute value is greater than or equal to the real number itself, so you get that other inequality also. Similarly, you get one involving imaginary part, which stems from a similar inequality where on this side you have imaginary part of z. And then we have our usual triangle inequality, which is the exact replica of what you have for real numbers. The absolute value of the sum of two complex numbers is less than or equal to the sum of their absolute values. This can of course be proved from scratch. That means where you consider the actual definition of addition, the definition of absolute value, but there is a geometric way of at least seeing instantly why this works and also why it's called triangle inequality. Suppose your complex numbers z1 and z2 are located here and here in the complex plane. Like you want to locate z1 plus z2. To do that, you use the vector representations of complex numbers. This vector represents z1, this one represents z2. So first you take their sum using the parallelogram law of vector addition. You complete this parallelogram and then this diagonal will be the sum of those two vectors, and hence the tip of the diagonal will be where z1 plus z2 is located. And now you look at the inequality. The left hand side is nothing but the magnitude of this vector or the length of this diagonal, and the right hand side is what? This length, which is this, plus this length, which is mod z2. But this mod z2 is also equal to this length. So the triangle that you are having here has its side lengths in the inequality. This side length is the left hand side. This side length of course is just this one, and this side length is this. So the inequality is telling you something that you already know from geometry, that the sum of two side lengths is greater than or equal to the side length of the third side. So in that sense, the inequality should be true. But the problem here is that, you can take this as a proof of this inequality, a geometric proof. The problem is that you will have to consider many cases depending on where these complex numbers are located. You will have to see, the thing you have to make sure is that you don't miss anything. When working with geometric things, there is always a possibility that you are missing something. You are missing some case. And if your proof depends on many cases, then already there is a high chance that you will miss something or you will make mistakes. Instead, it's much better to actually apply the definition of addition and absolute value and work out an algebraic proof, which is why algebraic proofs are generally preferred if the definition itself is algebraic. The authors have not given any proof of this inequality, which can be called a proper proof. Maybe in the exercises they have asked us to prove this, I don't know, I did not see it properly. Actually, we are not going to see exercise solutions for the exercises that appear at the ends of the sections in the first chapter. Okay, because this is the preliminary chapter and mostly we actually know these things. We are just reviewing these things as quickly as possible so that we can get to the main thing, which is complex functions, their differentiation, integration, those things, actual complex analysis. Now, just like you can extend the triangle inequality for real numbers, and have something like this. That can also be done for complex numbers, which involves not just 2 but any finite number of complex numbers. And the proof is a very easy proof using induction. It's given in the book, you can see it yourself. Besides this, there are also 1 or 2 more inequalities which I am not going to mention, which involve absolute values of complex numbers and difference. Okay, that also I am leaving to you. So in the next complex analysis video, we are going to see complex conjugates and if possible some other things also.